Alrighty. Let us wrap up momentum. And this will also be the last lecture that could possibly be on exam 2. Alright, so where were we? Let's recap the main ideas. Again, talk a little bit more about elastic versus inelastic collisions, and then do some problems. To recap, the ideas behind momentum was that how do you change momentum, this thing that I'm calling P, which I could define as the mass times the velocity, a vector quantity, PMV. You change it by impulses. Impulses are forces applied over time. These times could be very short, like a collision. These could be over long periods of time, like gravity slowly pulling something back down. So the expression to change momentum is the integral of force over time, or if, particularly in the case of a very short collision, you might sufficiently accurately represent that applied collision as some sort of average force over some amount of time. You could always define an average force, but in the case of a very quick, abrupt collision, it's actually pretty accurate. Contrast that with energy. How does energy change? Through work. Work is forces being applied over a distance. Forces either have to be acting parallel or anti-parallel, or have a component that is parallel or anti-parallel to the direction the object is moving. That changes the object's kinetic energy. Whether it speeds up or slows down, it is a scalar. It does not tell us anything about the direction, but it does tell us something about the magnitude or the speed of an object. These are two quantities that, if you pick your system wisely, are conserved. If there are no external forces on the system, then momentum, the total momentum of the system, is conserved. Add up all the individual momentums of everything inside the system, and momentum is conserved. This can be, what we mean by conserved could mean that if the external forces remain zero for long periods of time, then that means the momentum can be conserved between two widely separated points in time. The sum of the momentum must always add up to be the same. Or if there are external forces, you might be able to still use momentum conservation if you're considering a very short, very strong collision, in which case there really is only the collision really is the only thing dominating or determining what the motion is doing. So like a ball bouncing off a wall. Even though gravity is technically an external force, if I define the system as the wall and the ball, during that very abrupt time when the objects collide with one another, I could treat right before and right after the collision as 2 points where the momentum is conserved. Contrast that with, again, energy, which in this case, if the external forces do no work, and all forces are conservative forces in the system, then the total energy, kinetic plus potentials, is conserved in the system. So we saw that in the previous chapter. And how both these quantities change, again, one changes by forces over time, one changes through forces over distances. Usually you can change both. During an interaction, both can change. But sometimes, what happens during an interaction only changes one of these quantities, in which case you have to ask yourself what's going on with either energy or momentum. If for example, something comes to an abrupt stop. An abrupt stop means that both the momentum and the energy have gone to zero. But how they go to zero requires different arguments. Momentum can be brought to zero by forces acting over time. Energy can be brought to zero only if forces are acting over distances. So we could take the example of, the unfortunate example of someone gets in a car, someone loses control of their car, the car careens off the road, runs directly into a tree. The car then comes very abruptly to a stop, usually in a slightly diminished state. So the momentum of the car has gone to zero. It was originally moving in one direction and then suddenly it stops. So its momentum has gone to zero. So what got rid of the momentum of the car? But the kinetic energy of the car has also gone to zero. So what got rid of the kinetic energy of the car? In that case, we could take them one at a time. So the easier one is momentum. The car ran into the tree. The force of the tree, there was then a contact force with the tree that applied a very strong force back on the car over a short amount of time. That allowed the momentum to be brought down to zero very quickly. So the force from the tree being applied over a short amount of time, that contact force is what brought the car to rest in terms of its momentum. But if it's a big sturdy tree and the car just runs in and comes to a stop, there's no real movement going on. The contact force there is between the tree and the car. But nothing is really moving at that point of contact. The tree is staying here. The car has run now into the tree. But that point of contact really isn't moving. So in that case, the car has all this kinetic energy, but the tree is not doing any work on the car. But the velocity of the car clearly comes to zero. That kinetic energy had to go somewhere. Where did the kinetic energy go? So, usually in these cases, if it's a very light collision, your car has bumpers that compress a little bit. So there is a little bit of motion, say the compression, the contact between the tree and the car, the compression of your bumper, takes away, that is work being done. The energy of the car can be then instead stored as some sort of elastic energy that then likely gets dissipated as heat or something in front of your car and on the base of the tree. For a more violent collision, the fact that your car ends up in a fairly damaged state is because of energy. It's because your car had all this kinetic energy that it had to get rid of, but kinetic energy can only be eliminated through work. Things have to move, and so as a result, your car crumples. Things break. All of those individual motions is essentially it's a way for the car to get rid of its kinetic energy. The hoods of your cars are designed to crinkle for that very reason. That when you have a collision, the kinetic energy, two cars colliding, a car with a tree, usually there's very little motion in terms of at the point of contact. So work has to be done in some way to get rid of all that kinetic energy. So the hoods, the front ends of your car are designed so that they crumple up. All those individual crumpling motions allow for your kinetic energy to be dissipated away. And that is why your car gets so damaged. It's essentially your car is trying to get rid of all the energy that it has, kinetic energy that it has. So I have a demo I like to do here, which I call the yogurt drop. So here, let's take cars running into trees are unfortunate. Humans are involved in those cases. Let's take a simpler example of I'm going to take a Yoplait yogurt, open up the lid, stand very high off the ground, and drop it onto the ground. And drop it in such a way so that it lands flat on the ground and doesn't, go at an angle. So what's happening in this case? I go very high up, I release the yogurt container. The yogurt container falls to the ground. As a result, it's accelerating from gravity. It is gaining kinetic energy and momentum as it falls towards the ground. And then it hits the ground and very abruptly comes to a halt. So you have to ask what happened, where does the momentum go? Where does the kinetic energy go? So here my camera is set up on the ground. I am now climbing onto that table where I have my Yoplait container. The lid has been taken off. I'm now going to stand on the edge and drop the yogurt container. One more time. So it all happens pretty quickly. Then we're going to see it in slow motion. So it all kind of happens right here in the center, near the bottom and the center part of the screen. So the container comes to rest. Now here's at half speed. While the container comes to rest and gets rid of its momentum by being in contact with the floor, the kinetic energy cannot be dissipated in the same way. The container is not really changing shape when it hits the ground. So the container, yogurt plus container, has all this kinetic energy that it can't get rid of. So as a result, the yogurt, with all of that kinetic energy, tries to go in some other direction, in which case the yogurt takes the path of least resistance, in which case the yogurt shoots back up into the air. Now in the analogy of a car hitting a tree, right, the car is the yogurt container, you are the yogurt. And that kinetic energy, you have to get rid of your kinetic energy somehow. In the case of you, during a car accident, your airbag inflates. It is applying a force, and you kind of sink into the airbag. So you are getting both work and impulse are being done on you in order to slow you down with the airbag, for example. And we hope that the airbag is there, else something else is going to have to provide that impulse or work to slow you down. All right, we had talked a little bit about collisions, speaking of collisions, which could be elastic or inelastic. Remember, the inelastic collision was one where kinetic energy changed from one, pre and post collision. Inelastic collisions, kinetic energy is typically always lost. Actually, I don't think it's possible for the kinetic energy to increase, really. Unless it's contrived in a way. So usually, right, you throw a ball against, you drop a ball, it bounces off the ground. Every time it bounces, it doesn't bounce quite as high. In that case, it's because there is kinetic energy that's being lost. Work is being done by the ball. Where is one of my balls? By the ball, compresses when it hits the ground, and then when it launches back up into the air. But that compression, heats up the ball. There's a little bit of heat, and there's some friction that then causes the ball's total energy to slowly decrease with time. As opposed to an elastic collision where they both momentum and kinetic energy are conserved. Often we will be dealing with inelastic collisions, like when things stick together. Those are mathematically a little bit easier to handle. But for special cases, we can write down what the solutions are for elastic collisions as well. So let's go back to, I guess it was 2 lectures ago, where we have a cart of mass m, and it's moving at some velocity v, and it runs into another air cart of mass m that originally was stationary. In this case, we saw, I can just play it again real quick. In this case, we saw that the motion seemed to be exchanged with the object. One was moving after the collision, the other one was moving. During this elastic collision. It's elastic because there's little, you can't really see it, but there's little springs at the ends so that when they collide with each other, the collision is elastic. So it seems like this was pre, and then post was that this M had 0 velocity, and then this object had some non-zero velocity. So we could try to write that down and convince ourselves that that's the case. Again, I'm going to define my system as the two objects pre and post collision. So I can analyze the momentum and the energy of the system pre and post collision. Since these are all happening horizontally on a frictionless air track, actually I could look at this as a function. I could look at this at any 2 points in time, but really what we're focusing on here is the pre-post collision results. So the sum of the momentum pre-collision is just going to be m, and I'll say this is v naught. Let me see, I'll call that v naught. And then the other object is not moving, so its momentum is m times 0. So the initial momentum of the system is mv naught. And then post, the first object might be moving, the second object might be moving. We've seen from experiments that it seems that v1 in this case, the post speed velocity of the first object, the one that was originally moving, goes to 0, and v2 goes to v naught. So let's actually prove that that's the case. But right now we won't make any assumptions about what's going on. Since this is also 1D, I'll also drop all the arrows. Though, of course, whether the velocity is positive or negative still has meaning in this case, whether it's moving to the right or to the left. And I suppose we can say to the right is positive. So momentum conservation then says that mv naught equals mv1 plus mv2. Or, since m's a bound, v naught equals v1 plus v2 from conservation of momentum. Conservation of energy says that the total energy prior to the collision is just 1/2 m v naught squared. And then the total energy post-collision might be 1/2 m v1 squared plus 1/2 m v2 squared. If either of them are moving or both of them are moving, there's kinetic energy associated with that. So we need to consider each of them having their own kinetic energy term. In this case, m's a bound, so I can set these equal to one another. M's a bound, 1/2's a bound. So what this says is that v naught squared equals v1 squared plus v2 squared by conservation of energy. Alrighty. What I'm going to do now is I'm going to take the first expression, and square it. So I'm going to take v naught equals v1 plus v2, and I'm going to square both sides. So we got this from conservation of momentum, but now I'm squaring it. So that implies v naught squared equals v1 squared plus v2 squared plus 2v1 v2. But conservation of energy says that v naught squared equals v1 squared plus v2 squared. So those two things I just highlighted in blue are the same thing. So this is the same thing as saying that 0 equals 2v1 v2. So what we've arrived at saying that v1, v2 equals 0. which implies either v1 equals 0 or v2 equals 0. Just by, I forget what this rule is, if it has a name, but by math. By the way multiplication works. All right, so we're almost there, because this implies essentially there are two possibilities, and now we have to argue what the possibilities could be. And here we have to argue a little bit via physics. We said by the center of mass relation, and I'm actually going to restore the arrows, that the initial momentum of the entire system, capital P, was mv naught. Particularly, it's a vector, and this is a vector that points to the right. Originally, if I looked at the system and considered the momentum of both objects, one wasn't moving, the other one was moving to the right. Overall, the entire momentum of the system is moving to the right. Since momentum is a vector quantity, that also has to be taken into account when you apply conservation. To say that the momentum after the collision is the same means that not only is the magnitude the same, but that the final momentum of the system must also be pointing to the right. Both direction and magnitude are conserved with momentum. So that means that after the collision, something has to be moving, and it has to still be moving to the right, because the momentum prior to the collision was pointing to the right. The momentum after the collision must also be pointing to the right. And so it makes sense that only way for this to happen is if v1 is 0, v2 then is v naught. The first one, why does v1 have to be 0? Because if it was not, if that was not the one that was 0, then that means v2 would have been 0, and the cart would have been collided with cart 2, but then still also be moving to the right, while the other one's not moving, which would mean it's passing through the other cart, which is odd. So then cart 2 must be the one that's moving. And by conservation of momentum, it must be moving with a speed v naught, so that the momentum before the collision, mv naught, equals the momentum after the collision, mv naught. Your book derives the general case where the two masses are not equal to one another. In this case, a lot of things simplify because the masses were the same. Let's see, where am I seeing this? But in the case of when both masses are different, your book derives it. And let me just write down the answer. Again, your book does this. And this is again a case where you have m1 coming in at v naught and colliding with m2, which initially was stationary. In this case, for an elastic collision, it's still okay to solve these two expressions of conservation momentum and energy to get the final velocities for both the objects. Now, are we going to need these equations a lot? No. But with these, we can replay some of the examples we went through a couple lectures ago and see if this makes sense. Going back to some of the movies we saw with collisions on the air track. So obviously, this one better give us the same answer we just derived if they have equal masses. So if m1 equals m2, we better get the same answer as what I got before. And notice that we do. If I look at v1, there is an m1 minus m2 in the numerator. So if they both are the same, that difference is 0. So then v1 equals 0. In the case where they're both the same mass, there's a 2m on the top. m1 plus m2 is also just 2m in the denominator. They cancel. v2 is just v0, like what we had before. So that's good. What if you had a massive target where m2 is enormous compared to m1? That might be what I said. I think I had a bowling ball is at rest. I throw a marble at it. What happens to the motion of the bowling ball and the marble? This could be I throw a ball against the wall. The massive target would be the building, the wall, and then the less than the object that's moving would be the ball, which is obviously much less massive. Finding these very simple, intuitive examples that you can have in your mind can be helpful. Like in the case of the ball and the wall, clearly when I throw a ball against Galileo Hall doesn't start moving. So I might think that I should anticipate that the velocity of the ball, or m1 in this case, the object that was originally moving, might be something similar to what it was prior, but moving in the opposite direction. It might bounce off. Versus the motion of the more massive object doesn't really move at all. So in this case, we have to make some approximations. And since I'm actually out of room, let me copy this over to a new page. So we could look at v1. v1 we know in general is m1 minus m2, m1 plus m2, original velocity. Now m2 is supposed to be enormous compared to m1. So m1 plus m2. If m1 is tiny compared to m2, so this might be m2 is 1,000,000 kilograms, and then m1 is a gram. If I add these together, they essentially do not change. It essentially is still just the mass of the big one. You think this is money. You have $1 billion, I give you a penny. You essentially still have $1 billion. The penny is not considerably changing the sum of your penny plus your original wealth. Okay. Similarly, m1 minus m2 is essentially just minus m2. I take 1 and I subtract 1 billion. My answer is essentially negative 1 billion. It's not exactly, but it's pretty darn close to negative 1 billion. So in this case, I can simplify. v1 is then approximately, the numerator was negative m2, the denominator was positive m2, v0. The m's cancel. I get that the velocity of the small object, the ball that hit the wall, is approximately pretty decently approximated by just being that it's moving at the same speed but in the opposite direction. It bounced off the object. Versus for v2, which is 2m1 over m1 plus m2. So again, I'll just replace that with m2 since m2 is enormous compared to m1. Now in this case, it doesn't simplify to anything, but we can look at the numerator and the denominator. You have a tiny number divided by an enormous number. 1 divided by 10 to the 9, for example. That fraction is incredibly, incredibly small by saying that m2 is much bigger than m1. So this is very, very small, essentially 0. The big object, it might get a tiny bit of motion, but barely. And we saw that, actually we did not see that. last example is you might have a massive projectile. I have a marble sitting on the table and I throw a bowling ball at it. So in this case, M1 is much, much bigger than M2. In this case, V1 is approximately, the numerator was M1 minus M2, but M2 is tiny, so that's approximately just M1 in the numerator. And then approximately M1 in the denominator, V0. So essentially it approximates to just being V0. The marble does not influence the bowling ball. I throw a bowling ball forward, it hits a marble, the bowling ball just keeps going as if the marble wasn't even there. Versus V2, which was 2M1 plus the sum. So the sum again just becomes M1. So in this case, this approximates to about 2 V0. The marble essentially goes along for the ride. It gets pushed ahead of the bowling ball when the bowling ball smacks into it. Or in the case of, a semi-truck hitting a car, the car then just goes along with the semi-truck, essentially unimpeded. The object plows right through. So I think what we saw with collisions, we saw the case where M1 equaled, say, 2M2, or for example. So maybe I'll write that down because there's a movie that we can show for that. So then V1 equals, let's see, was M1 minus, I'll just write down. That was the original answer. But now M1 is twice M2, so I could just plug that in. 2M2 minus M2, 2M2 plus M2, V0. The numerator becomes M2, the denominator becomes 3M2, V0. The M2's cancel. This is 1/3 V0. So if I have an object that runs into something that is twice as massive, notice here it's positive 1/3 V0, so the small object keeps going forward, but not as fast. Now it's going forward at 1/3 the speed. And then V2 was what? 2M1 over the sum V0. So that becomes 4M2 plus 3M2, or over 3M2 rather. So this is 4/3 V0. All right. So in this case, the more massive object launches forward at a speed 33% of the speed that the original object was moving. And I think we had a video showing that. So let's see if this is the correct one. So here's the more massive object, here's the lighter object. Didn't quite give us the right answer, did it? But notice she also, the air track is so hard because it's uneven. The fact that this object was also slightly moving, I think, is what's throwing things off here. Notice it was slightly moving to the right, so it wasn't actually perfectly stationary. Yeah, these are hard to do. The air track is hard to set up. But let's see, then I think she does the reverse. Is that correct? So let's see what that looks like. So, oh, I'm so sorry. This is what we just did. This is what we just did the numbers for. So, okay, physics still works. We wrote down that M1, the object that was originally moving, was twice as massive as what it runs into. So this is the setup for what we were doing. Apologies. So let's start back here. All right. Okay. So here we go. The more massive object hits the lighter object. The second collision doesn't matter. Notice that they both still kept moving to the left, but the smaller guy kind of just launched forward, while the heavier guy was still moving to the left, but not nearly as fast as it was moving before it collided the first time. All right, I then leave it to you to switch it. Have the thing that's stationary be the massive object, and then have the smaller guy run into the more massive object. Then you should get that after the collision, they both move in opposite directions. All right. That's all I had to say about collisions, which is maybe more than I meant to. Let's do some problems. Let's see. So there were a couple that stuck out to me as possible good ones. Though, of course, you should always try to do more. Now let's do an impulse one. So how about 25? Problem 25 of the book. A 1.2 kilogram ball drops vertically onto the floor, hitting with a speed of 25 meters per second. It rebounds with an initial speed of 10 meters per second. What is the impulse? And if the ball is in contact with the floor for 0.02 seconds, what is the average force from the floor on the ball? So the ball is moving down at 25 meters per second right before it collides. And then post-collision, it rises back up into the air initially at 10 meters per second. Of course, you cannot see any of this. It's saying initially because, of course, if we waited long enough, gravity would start to do other things. So we're looking right before and right after the collision. If I define my system as ball plus floor, then if I look in that very short amount of time when only the collision really is the only thing doing anything, I can say that there are no external forces, right? There's not enough time for gravity to do anything. And plus, as we will see, the amount of force that the floor is exerting on the ball far exceeds what gravity is doing to the ball over that short amount of time. And then the mass was 1.2 kilograms. So I could do this with momentum conservation. I could just do this with impulse. Maybe I'll just do that. Right, so I know the ball changes, the momentum of the ball changes as a result of impulse. But the change in momentum, delta P, is P final minus P initial for the ball. And let's see, let's define up as positive. So the final momentum of the ball was m times plus 10 meters per second. The initial momentum of the ball was m times negative 25 meters per second. Again, negative because we're dealing with vectors, and the initial velocity was pointing down in our coordinate system. So then this becomes 35m, which then is it's actually a nice number, 1.2, 20%, 42. 42 kilograms meters per second. That is what we would say is the impulse on the ball from the floor. If we approximate the impulse as the floor exerting an average force over some amount of time, then we can set that equal to 42 kilogram meters per second. It's a delta T was 0.02 seconds. Then the average force then is 42 divided by 0.02, so 2100. Technically plus 2100 newtons. Plus, because it's a vector, there's an average force from the floor on the ball pointing upward, which is what then allows the ball to change direction. Because then there is a quite large acceleration that the ball feels pointing upward. Next, I have 39. On my room. Moving over. So book problem 39. A 91 kilogram man lying on a surface of negligible friction shoves a 68 gram stone away from himself, giving the stone a speed of 4 meters per second. What speed does the man acquire as a result? So you could think that this man is doing this on an ice rink. I'm standing on an ice rink, I have a stone, I throw the stone in one direction. What does my motion become as a result? So maybe we'll just draw it as I'm standing on ice. So what did it say? 91 kilograms. The stone was 68 grams. 1, 2, nope. Or 0.068 kilograms. And then he throws the stone. So that now the stone has a velocity of 4 meters per second to the right. Let's define right as positive. What is the velocity of the man as a result? Now this is an experiment you would try on your own. If you go to an ice rink, next time you go to an ice rink, bring a bowling ball, roll the bowling ball away from you as when you're on the ice rink, standing perfectly still, see what happens to your motion. Here, let me define my system as person plus stone. And I'm going to look pre and post throw. In that case, I could say there are no external forces changing my momentum because I'm not allowing gravity really enough time to do anything. I'm just focusing on the minute, not the minute, the literal second as I toss the ball in the vertical direction or in the horizontal direction. Technically, I don't even need to do that. If we just focus on the horizontal motion, this is true for any point in time. Maybe actually I gotta say that. Since, because again, remember, momentum is a vector quantity, so you have to consider this question for every component. So I could say since the external forces are 0 in the x direction, total momentum is conserved in the x direction. So in this case, I could write down what is the pre-total momentum in the x direction, which is a vector. So initially I'm standing still and I'm holding a rock that is not moving. So I would say the total initial momentum is 0. Neither I nor the rock are moving. Then post-throw in the x direction, we're trying to determine if the man has any motion. If he does, then there'll be some momentum associated with the person. But then we do know the stone does have some momentum. And I guess since this is all in the x direction, I could get rid of those arrows. So velocity of the man in the x direction, velocity of the stone in the x direction, which we know the mass is, and we know that. We're trying to figure out whether or not there is any motion here. Conservation of momentum allows me to say that the total pre in the x direction equals the post total in the x direction, or that 0 equals mv plus m stone v stone. Which is great, because I just said that we know everything except one of these quantities. We can solve for the velocity of the person. In this case, it's minus m stone v stone, all divided by the mass of the man. So this negative means it's pointing in the opposite direction as the velocity of the stone. So since the velocity of the stone, we're going to say is positive 4 meters per second. Then this, I think, becomes, this one I did do in advance, I think it's 0.003 meters per second, something like that. Actually, I'm not confident that I did that correctly. I could just quickly check. Some mental math is easier than others. So mass of the stone, we said was 0.068 times 4 divided by 91. 0.00298. Oh, go me. Right, so the velocity of the person is non-zero. It's not large. It's not 4 meters per second, but they are moving a little bit to the left. So I throw the rock to the right. I, as a result, also start moving a little bit to the left. You could think of that in terms of forces if you wanted to. You could think of, well, that's Newton's third law. I acted on the stone to make it move to the right. The stone acted on me to make me move to the left. Okay, then I have a version of number 17, which I said I would do last lecture. So suppose here's the dock. And you're in a boat. I think actually the problem assumes that there's a dog. So suppose there's a dog that's sitting at the end of the boat, which is right next to the dock, and the dog walks to the other side of the boat to get off the boat. The question is, where is the boat once the dog walks to the other side of the boat? So I think it says that the mass of the dog is 4.5 kilograms. The mass of the boat is 18 kilograms. The length of the boat, so we'll call this length here L. The length of the boat was 2.4 meters. And then that's all it says. And it says, yeah, the dog walks to the other side of the boat, and essentially is asking where is the boat located relative to the dock. So if you want, you can also assume, we could say, like, let's suppose the dog, turns out this number doesn't matter. Let's suppose the dog does this in 2 seconds. Just to put some numbers down. And we, of course, have to treat the water as not a contributor to anything in the horizontal direction. Let's assume it's a nice, calm lake. There is water is pushing up on the boat, but is not acting in the horizontal direction. So in this case, I would say my system is going to be boat plus dog. I'm picking that as my system because those are the two objects that are interacting with one another. So that's really, when I'm thinking about momentum, I'm usually looking at interactions between two things, and I want to define my system as those two interactions. So if this is my system, then there are no external forces in the x direction. So I can say the total momentum in the x direction is conserved. And that it's conserved, before the dog starts moving, after the dog gets to the other end of the boat and stops moving, and then also during the intermediate time where the dog is actually walking. And we could write that down. I could say, okay, what is the total momentum before the dog moves? In that case, the boat is stationary on the water, the dog is stationary on the boat. The total momentum in that case is 0 in the horizontal direction. Then I could ask, what is P while dog walks? So then we have some dog, which has some velocity, v dog, in the x direction. Get rid of these vectors. Plus the mass of the boat times the velocity of the boat, which might have some motion as a result. Now in this case, the velocity of the dog we can approximate as, well, I guess we have to make a choice. Is left positive or is right positive? Let's say right is positive. So then I would say the velocity of the dog in this case might be something like negative L divided by delta t, right? If it covers 2.4 meters in 2 seconds, and we approximate that the dog is walking at a constant rate, we might say that whatever 2.4 divided by 2 is, I guess 1 point. So negative 1.2 meters per second. Is the velocity of the dog. So by momentum conservation, the initial total momentum is equal to the final total momentum, which means that 0 equals m dog v dog plus m boat v boat. So that the velocity of the boat is non-zero. So actually it's essentially the same problem as the person throwing the stone. So in this case, right, we could get a number if we wanted to. The negative, so it's a negative 1.2. So 1.2 times mass of the dog, 4.5 divided by 18. I get as positive 0.3 meters per second. Positive meaning the boat is moving to the right, inconveniently away from the dock. So after 2 seconds, the boat has moved 0.3 times 2 is 0.6 meters away from the dock. Inconvenient, indeed. And again, this is, you could think, is this magic, or, can I relate this back to forces? Again, momentum is deeply, deeply connected to Newton's third law. The dog is pushing on the boat to make the dog move to the left. The dog is pushing down so that the surface of the boat, or friction with the boat, is pushing the dog to the left, allowing the dog to accelerate and move to the left. So by Newton's third law, the boat is feeling a push to the right from the dog. And as a result, the boat starts to move to the right. Suppose then the dog gets to the end of the boat and then just stops. What is the total momentum after dog stops at the end? Well, the dog itself has stopped, but is the boat still moving in any way? And it cannot, because momentum is still being conserved. So if, initially it was 0, so this must also add up to 0. But if the dog is not moving, then that suggests that the boat stops moving. Once the dog gets to the other side and stops moving, the boat also stops moving. Again, if you want to think of this in terms of forces, the dog had to stop itself from moving to the left, so it had to feel a force pushing it to the right. It put its foot out and pushed down on the boat to stop it from moving forward. As a result, the boat felt an equal and opposite force in the other direction. What fun. Now, in many cases, many real world problems, applying just Newton's laws or just conservation of energy or just momentum is not enough. Sometimes you have to do both, or rather use multiple parts of that to solve a problem. Suppose I have a 1/2 kilogram pendulum bob. So this mass is 1/2 kilogram. And this has a length of 70 centimeters. And I release it. It rotates down and smacks elastically into a box, where the box is 2.5 kilograms. And collides elastically with the box. If it's on a frictionless surface, that guarantees that the box will start moving to the right, and I could ask, with what speed does the box start moving to the right? Now in this case, we cannot just apply conservation of energy or conservation of momentum. We can apply both, but we have to do it in steps. So if I look at this system, I see, a pendulum just swinging down in a quarter of a circle and hits the box. So I would say step 1 is the pendulum swings down I would say under gravity, and there's some tension in the string. If I analyze let's take the case of the pendulum has already moved down a little bit, so it's now at some angle. What is the free body diagram of the mass at the end of the pendulum bob? Gravity is pulling down, of course, and then there's tension that is pulling up the string. All while the object is moving, it's moving essentially through a quarter of a circular arc. Which is great because that means that there is a 90-degree angle between the direction the object is moving and the tension force. So I'd say T does no work. Only Fg does work. We can apply conservation of energy to the motion of the pendulum. Thinking ahead, we could ask, why is that useful? that would allow us to say, if the bob is released from rest, it would allow us to say what is the motion, what is the speed of the bob right before it collides with the box. And then we could use momentum conservation to think of what is going on during that very brief collision with the bob in the box. So for this part one, I would say, okay, total energy is conserved. Kinetic plus potential is a constant. The total energy prior, the bob was released from rest, and it is some height off the ground. Since this is a semicircle arc, we know that that height is going to be 70 centimeters off the ground. Then the final total energy, it has some kinetic energy, and then it's has gone down a height h, it's now to the ground, there's no gravitational potential energy. Conservation of energy says that they are equal to one another, so that 1/2 mv squared equals mgh. Or that v squared equals 2gh, or that v equals root 2gh, which is about 3.7 meters per second. Remember, technically this is the magnitude of the velocity, so it's always a positive number. And we really don't know anything about the direction based on energy arguments, though we could tell, in this case, it is going to be moving to the right. Then 2, I could say collision with pendulum and the box. In this case, I would say my system is pendulum plus box. In the horizontal direction, there are no external forces. That tension is pointing upward, gravity is pointing downward, so I don't care. I'm not going to ask about momentum in the vertical direction, but in this case, there is no external forces in the horizontal direction. P is conserved in the horizontal direction. So prior to the collision, I could say that the total momentum, the box is not moving, but the pendulum is. So I could say the mass of the pendulum times the velocity of the pendulum. Technically, and this is now, we now write this as plus 3.7 meters per second, where the plus now means to the right. You know, let's define right as positive as usual. And then after the collision, you go right that the total momentum is, there might be some final motion for the pendulum, and there is some final velocity for the box. And the conservation of momentum allows me to set these equal to one another. So mass of pendulum times v pendulum, and I'll just highlight that we know both of those numbers, equals mass of the pendulum times the final velocity of the pendulum plus the mass of the box, velocity of the box. Unfortunately, we're not done yet because we can't get a unique answer yet. There are two velocities we don't know. When the pendulum hits the box, the pendulum might also start swinging back in the other direction. It might bounce back. So we're not quite done. Then, of course, we can use the fact that this is an elastic collision. Which says that the kinetic energy before, which was just 1/2 m pendulum v pendulum squared, equals the kinetic energy after. So 1/2 m pendulum, the final pendulum velocity squared, and then 1/2 m box, the final velocity of the box squared. And these, therefore, are equal to one another. So that says mp vp squared equals mp vp final squared plus m box v box squared. Where again, I don't know these velocities, but now that I know everything else, you can simultaneously solve both of these expressions and get, take one, solve it for one of the v's, plug it in the other, get a number, then use that to get the other number. You've done a couple homework problems like this. So what I get, assuming I did not make a mistake, is that the pendulum final velocity is about negative 2.47 meters per second. So it does bounce back, but notice it does not bounce back with 3.7 meters per second of speed. And then the box has some forward motion of plus 1.23 meters per second. So it starts moving to the right at about 1.23 meters per second. I'm about at am I at an hour and 5 minutes? A little over. If you want to stop, you can stop. I'm going to do maybe one, maybe two more problems. How much room do I have? Let's do another one where you have to combine conservation and of energy and momentum. What has happened? So suppose I shoot a bullet that is moving, there's some mass of a bullet that has some velocity. It bores and lodges itself into a wooden block that is hanging by a string. As a result, the string starts to the box and the string start to rotate, and the box swings up a certain amount. Particularly, it raises some height h. And the question is, how high does the box lift into the air as a result, as it swings from the push that I got from the bullet lodging itself in? All right, so in this case, I need to give you some numbers. So let's assume the mass of the bullet is 0.00. I can't read my own writing. I think that's a 0.05 kilograms. That's a very light bullet. I think that might be a 9. This might be so about 10 grams, or about 1 gram. Yeah, about 10 grams. If your math is off by a factor of 10 or thereabouts, that might be why. The mass of the block, or the mass of the wood, we'll say is 5.4 kilograms. The height is unknown. The speed of the bullet is about 630 meters per second. And the question is, how much does the object lift into the air? Now, the first step would be to look at, there's kind of two phases of this interaction. The bullet comes in, collides with the block, and lodges itself. At that point, block plus bullet swing. So I might say the first thing to do is to look at the collision of bullet with block. In this case, this is an inelastic collision. Or a rather sticky collision. So this is my system. Again, everything is acting in the horizontal everything in the horizontal direction has no external forces. So F external in the x direction is 0. I can again apply momentum conservation in the horizontal direction. So I'd say the total momentum prior is just the mass of the bullet times the velocity of the bullet. It's defined to the right as positive. And then P after the collision is going to be the mass of the bullet plus the mass of the wood times whatever velocity that wood, so we'll call it, bullet wood. Both the bullet and the wood now are kind of, essentially you can think of it as just one object that is now starting to move as one, with some horizontal, initially purely horizontal motion. The rope, of course, then changes that a little bit, but in conservation of momentum says that you can set these equal to one another. So m bullet v bullet equals m bullet plus m wood v wood and you can get some expression for the velocity of the system. So let's see, the bullet we said was 0.0095, we're going to say. Yes, I'll just recalculate these since I don't know if my other numbers are correct. And then that was multiplied by the velocity of the, so 630 divided by the sum of the two, 5.4 plus 0.0095. So then I get this is about 1.11 meters per second. Technically plus, yeah, because it is moving to the right. And now, before I flip to the next page, actually, let me see. Maybe I can salvage this. Move this up. Move this up. So now I would say phase 2 is the swing. So again, my free body diagram of the block bullet has gravity pulling down and tension pulling along the string. Though again, the object is moving kind of moving in a circle, or is confined to move as a circle. Which again means that the tension force is perpendicular, does no work, only gravity is doing work, conservation of energy applies. So in that case, I could say the initial total energy, which is 1/2 m block plus wood, v block wood squared, equals the final kinetic energy, which if we're asking how high it got, we're looking for that momentary point where it stops moving. So there's no kinetic energy, but bullet plus wood has raised some height into the sky. Where here, I guess I called the ground just the initial height that the bullet block started at, and then it raised up h above that. So this is good because I know everything. I can solve for h. the masses cancel, so that's always convenient. So it looks like it's v squared of wood bullet divided by 2g. Gives me h, which let's redo the calculation. So 1.11 squared divided by 2 divided by 9.8. Oh dear. Divided by 2 divided by 9.8. I get 0.063. So again, the first step is to apply conservation of momentum, and then after that, use that to get some number that you need to then apply, in this case, conservation of energy. Okay, good stuff.